One of the more dangerous things we'll do, dehydration. Let me make sure I get the spelling right. The dehydration of sugar. So we take sucrose, so table sugar, and react it with sulfuric acid. The sulfuric acid has to be highly concentrated. So what's the equation for table sugar, also known as sucrose? We did it all yesterday. So what's the subscripts? 12, 22, and 11. Sulfuric acid. What's the formula for sulfuric acid? Allie, you were so good at it. KCl. KCl? No, sulfuric acid. That's potassium chloride. So acid tells you we have H plus ions. Sulfuric, the ick, tells you what ending for the alky ion? 8. So this is hydrogen with sulfate. And what's the formula for sulfate? So we have H plus, and what's sulfate's formula? So 8 is usually O3 unless it's sulfur and phosphorus. This is sulfur, so it's SO4. What will be the charge? So yes, -2. So sulfur is in the 6th group, so it gets +6. There are 4, -2. Add those together, and you get -2. So this is a 2-to-1 ratio. So the formula is H2SO4. Again, sugar is not ionic, so we can't just simply do double displacement or replacement. I keep saying displacement. It's replacement, not displacement. I don't know why I have it stuck in my head. I've said it wrong my entire life. I guess it's because I always thought my teacher was saying displacement. It's replacement. It can't be double replacement because this is not ionic. But from the name, what do you think this is going to do? The reaction is called dehydration of sugar. What does the word dehydration mean? What do you think from the name dehydration means? What does it mean to be hydrated? What? To have water. And what does dehydrate mean? So to remove, be more scientific than water, H2O. Look, we have H2O. Actually, how many H2Os do we have? We have 11 of them attached to 12 carbon. So if I remove the H2Os from carbon, what am I left with? Carbon. I'm left with 12 carbon and 11 H2Os. And then what am I missing? I guess I shouldn't do, missing some sulfur. So usually the equation is more written like this. We have C12H22O11, and we put acid right here, and we get 12 carbon and 11 water. Like this. The full equation, however, is what I was starting with. This reaction requires some oxygen, and it still makes the carbon. And water. During the reaction, however, this is going to attack some of the carbon, making CO2 gas and sulfur dioxide. So even though sugar can dissolve in water, it's considered a solid because it's not because it doesn't dissociate in ions. An acid is always aqueous. O2 is a gas. And this is going to be a very weird notation. I'm going to put half right here. And that's balanced. Usually, you never put halves. There is an exception that's usually done, and that's if you have one diatomic molecule on the problem that you only need half of it. Instead of multiplying this whole thing by 2, you can see it written like this. So let's see. Which one is the best to work with? So this is an oxidation reaction. Even if I remove the half, I'll temporarily do it just to make it clearer. But this is not a notation we're used to. Now remove whether or not it's aqueous. You usually don't write this equation like this. They actually keep the half in there. But is this equation a redox reaction? All right, let's analyze a few things. What is the oxidation number of carbon, or what's the oxidation number of hydrogen? It's always plus 1. What is the oxidation number of oxygen? -2. What is the oxidation number of hydrogen here? Plus 1. What is the oxidation number of oxygen here? 0. Very good. Even though I always say it's -2, the exception is when it's by itself. What is the oxidation number here for carbon? What about hydrogen and water? Oxygen, -2. Oxygen here, -2. What would the carbon thus have to be? So we have wherever carbon is, plus 2 times -2, and this is a neutral problem, so it has to be 0. So that'd be carbon minus 4 has to equal 0. Carbon is equal to plus 4. Same thing, or similar. What about oxygen here? Well, it's always -2 unless it's by itself. What would sulfur be? So what group is... So, yeah, sulfur would have to be plus 4. What about oxygen here? -2. It's always -2 unless it's by itself. And what would sulfur be in this? So ignore the coefficients, but you need to look at the subscripts. So we have 2 plus 1 plus whatever sulfur is plus 4 times -2. This is neutral, so it has to equal 0. So I have 2 plus S minus 8 is equal to 0. That's 2 plus S is equal to 8. S is equal, minus 2 from both sides, plus 6. What would carbon be over here? So again, we have whatever carbon is, plus 22 times plus 1, plus 11 times -2 has to equal 0. So that's whatever carbon is, plus 22 minus 22 has to equal 0. 22 minus 22 is 0, so carbon is 0. So, did any oxidation numbers change? Well, all the carbon over here is 0. Some of the carbon goes to 0 right over here. But some of it went to plus 4. Increased. So it was oxidized. Hydrogen plus 1 plus 1. Hydrogen plus 1. Hydrogen is not contributing. It's a spectator. Oxygen. We have oxygen -2 and -2. And do we have any... So we have some of the oxygen at 0. Is any of this is any oxygen on this side 0? So that means we can randomly pick one. We don't know what's going to. It's more complicated to figure out which one, but let's assume it goes to water, for example. We don't know exactly what this oxygen's doing, but it's being decreased, so it's being reduced. Regardless, we know that O2 is being reduced. Sulfur, did sulfur change? Sulfur is plus 6, plus 4, so it was reduced. What else? Hydrogen is plus 1, plus 1, plus 1, plus 1. So clearly we have some oxidation going on. Carbon is being oxidized. So this is most definitely a redox reaction. What does redox mean? It means energy is going to be released. And it's going to produce heat.
So if carbon gets oxidized, is it an automatic redox or?
Yeah, if there's any oxidation, if there's any change in oxidation numbers, it's redox. So this will get very, very hot, as that is a lot of carbon being changed. Actually, we can see that. So I like using the original one where it uses a half right here. We can see 11 carbon actually doesn't be changed. So 11 of this carbon stays 0. While one of the carbons is oxidized. The sulfur is always going to be reduced. So one sulfur atom is reduced. And one of the oxygens is going to be reduced. In it. So let's look at a video of this reaction going on. I did this last year. Or at least I tried it out last year before COVID. And I didn't get a chance to do it for my chemistry class though.
What's up, everybody? Welcome back to my laboratory.
This is a good video.
I got powdered sugar, but I don't think it matters what kind of sugar.
Alright, he's pouring sulfuric acid into a beaker of sugar.
What we're gonna do is mix it up.
And he's going to stir it and mix it up. It's getting hotter. And then you have pencil lead. That is pure carbon. With acid and water diluted in it.
We're going to try this again, but on a bigger level. So we're going to put the acid on that, and then we have to mix up the sugar. It's just a picture, man. Here. Okay, it's coming and coming.
Gives you an idea of how tightly packed the carbon and the hydrogen and oxygen are on sugar. As when you separate hydrogen and oxygen, the carbon has to rearrange itself into a different pattern, which causes it to spread out. And then, looking at it, we have a little bit of water, but mostly gas. The water turns into steam. It's actually gas too.
That experiment is pretty epic, but I can only imagine what are you guys gonna say.
That's one experiment I plan on doing.
Isn't it just like that? Oh, where did you get it?
The Black Snake fireworks. It's very, very similar, but it's This one's actually stripping water, H2O, hydrogen and oxygen off the carbon, while that one is another reaction. Were y'all in the rocket club? I gave Miss Parrish the instructions on how to make rocket fuel. I wonder if she did it. I have a feeling she didn't. That was boring. If you want to make rockets, it's very dangerous to do any of this at home. I'm choosing very, very nice looking ones. That have a great effect. But this is called amateur rocket fuel. I've made this, and the instructions whenever I was a kid when I made it says if solution turns black, run. And I look up, and my solution instantly turned black. I'm like, I probably should have read this way beforehand. Luckily, it didn't explode in my face. But potassium nitrate and sugar. So this is a combination of sugar again. You'll notice sugar. Why do y'all think I'm using sugar a lot? It has a lot of energy in it. That's the reason why we live. We live off of glucose. Our body has to consume glucose to make energy. But it's sugar and potassium nitrate. Sugar has a lot of energy in it. There's a lot of carbon bonds we can break. So, and again, I should specify what type of sugar. Sucrose. So C12, H22, O11. And what's the formula for potassium nitrate? So potassium is K plus. What is nitrate? So again, the 8 tells you it's going to be NO3. 8 always refers to O3 unless it's sulfur or phosphorus. It's not sulfur or phosphorus. Nitrate refers to nitrogen. What's the charge on it? Well, what group number is nitrogen in? It's in group 5, so we give it an oxidation number of plus 5 plus 3 times negative 2. Oxygen is always negative 2 oxidation number. And the sum of oxidation numbers gives you the charge. So, yes. And this is the 1-to-1 ratio. So we have KNO3. And let me write it again as this has crazy high numbers. So this is a solid. This is aqueous, though it doesn't matter as we're not dissolving it into water. What is this going to make? Good guess. I'm trying to think of a good way. This isn't going to be a good way to do this. I'll just tell you. The fact that this is covalent isn't very good. It produces potassium chlorate. Not chlorate, carbonate. CO2. Water. And nitrogen. Nitrogen is a gas. Water is going to be a liquid. CO2 is a gas. This is aqueous. What would be the coefficients? Hmm? Yes, N2. Nitrogen is diatomic. So again, start with something that only appears once on the left and once on the right. What's that something? Nitrogen? Alright. So we know that the ratio is going to be, well, there's one here and two over here. So we know it's going to be a 2 KNO3 to 1 N2 molecule. So whatever the number here is, this has to be twice as much. What's something else? Potassium. Well, there's one over here, one over here. So I know the ratio is going to be 2 KNO3 to 1 K2CO3. So if this number is 5, that means this has to be 10 and 10. So, oh yeah, okay, good. Hydrogen. So, what's the ratio here? It's 11 of these per one of these. So, 11 sugar to, or 1 sugar, I mean, to 11 water. Now we just need to balance carbon and everything will fall into place. So we have carbon appearing on the left. So I have 12 carbon. And that has to equal, if I look over here, 1 carbon. I will call this subscript X. Or I should say, I'm going to call this one X. It's a good thing to do. This one's complicated. We have to do oxygen at the same time. This would be trial and error mostly. You start with one, assuming 1 here, work it out. You see it doesn't work. Try 2 here. I'm going to just tell you all the formula. See if there's, I want to see if there's any quick way of doing this. So I know it's 12 carbon over here, so 12 times X, whatever this is. I'm going to assume this is Y and this is Z. That's what our... One way of doing this is assume A, B, C, I shouldn't choose C, D, E, put brackets so we know it. And you come up with algebraic equations for it. So I know that B is equal to, I know 2 times B is equal to 1 times F, right? I know that 2 times B is equal to C. And thus I know F is equal to C. So here's some equations. I know that 12 times A has to be equal to C plus D. That's another equation. I need to do an thing for oxygen. So I know oxygen is 11 times A, tells me how many oxygen are left, plus 3 times B, so 3 oxygens, and that is to equal 3 times C, plus 2 times D, plus E. And basically you solve the algebra using all these equations. That's too complicated to do in this class. These numbers are really big. 5, C12. You can do it by guessing and trial and error. Your largest formula will always usually be the smallest subscript too. But this is the formula. Look at how much gas is produced. And the water is actually going to be steam. It's going to quickly turn, but that's even gas. Look how much solid is produced compared to the gases. Y'all good? Or need me to go back? Potassium. So I've made some of this when I was a kid. I never put it into a closed tube and launched as a rocket. I just burned it. But lots and lots of gases.
Baking the jet fuel, something goes horribly wrong.
By the way, y'all should not do any of this at your house without complete knowledge on how this works. I'm using mostly my college experience at knowing how these things can go wrong. Basically, you caramelize sugar. That means you get it to melting point without burning it. And while it's mixed with potassium chloride. This causes potassium chloride, carbonate, no, nitrate, potassium nitrate to dissolve in the molten sugar and form a solid mass. But let's analyze the redox of this. So we know carbon is 0, plus 1, negative 2. We've already done this. Calcium would be what? Calcium is in what group? First of all, this is ionic. So it's going to produce K plus ions, so you should already know. But it's also in group 1 and it gets plus 1. Oxygen's always negative 2. What would nitrogen be? So we have KNO3. This is +1. This we don't know yet. This will always be -2. And the charge up here is 0. So the sum of charges, so +1 plus wherever n is, plus there's 3 of them, 3 -2's has to equal 0. 3 times -2 is -6. Moving the 6 over, 1 plus n is equal to 6. Minus 1 from both sides gives us n is equal to +5. Potassium is what? +1 is in group 1. Oxygen is always -2. What would carbon be? I believe so. So that'd be 2 plus 1 plus carbon plus 3 times -2 has to equal 0. So that'd be 2 plus C minus 6 is equal to 0. 2 plus C is equal to 6. C is equal to +4. And -2, that means this has to be +4. Hydrogen is +1, oxygen is -2, and nitrogen is 0. So we're all changed. When seeing an equation like this, almost always easiest to look at the gas, the diatomic molecule. If there's any diatomic molecule 0, we know it had to have changed. So this one has been reduced from +5 to 0. What is oxidizing it? So potassium hasn't changed. Carbon. Carbon is going from 0 to +4. All the carbon is going to +4. So it's being oxidized. Thus, nitrogen is our oxidizing agent. It's oxidizing the carbon. Which you would think it would be oxygen given how many oxygen are in there, but there's no O2 anywhere. So this produces a lot of heat and fire. We probably won't. I don't know about this one. Doing this one is just something I did before. It's a neat experiment showing gas being produced. The problem is you're making rocket fuel in a pan over a heat source. And it's without like crazy sensitive temperatures you're guesstimating. You get it too hot and you're floating around the flashpoint to where it just explodes in it. I definitely wouldn't make it with y'all, but I would, if I make it, we'll burn it. It's something I would make and we just light. What's the other one? This is the reason why I chose this one. I chose this one to do today because what what's the ratio I should mix these for the perfect fuel? So, I know it's going to be 5 sucrose molecules react with 48 potassium nitrate molecules. So the ratio is 5 moles of sucrose to 48 moles or molecules but we're not going to sit there and count molecules. Instead, we're going to weigh it out in grams, or you would if you make it at the house. So what is the molar mass of sucrose? Oh, we haven't done it before, but just Googling it real quick because we're running out of time. 342.3 grams per mole. And for potassium nitrate, it's 101.1032 grams per mole. But the subscripts are not 1-to-1. This is not a 1-to-1 ratio. So I want to. So even though I know that this has a grams per mole, I need 5 moles of this. So to get this into a ratio of grams to grams, I simply multiply by 5 moles. Moles cancel out. So 1,711.5 grams of sucrose. And 48 moles over here. Moles cancel out. Which gives me 4852.9536 grams. So this is the ratio. These numbers are too big. When you're cooking at the house, surely you don't ever read. You do 1,711.5 parts per every 4,852.9536 parts of this. What you do to get a better one is divide. So 4852.9536 divided by this number gives us a ratio of 2.8355. So that means we could do 1 gram of this for every 2.8355 grams of this. So the ratio is 1 to about 3. If you look up, this is not the ratio you should use. Does anyone want to take a guess of why this is? So theoretically, this is the ratio you should use. Why does a theoretical not work? This is the theoretical thing. So imagine the molecules are tiny little squares and circles. So I need 5 sucrose for every 48 of these. Sucrose is very big. So I need 5 sucrose, and I'll put little dots to make a reaction work. Now, as soon as they react with each other, a lot of energy is going to happen, and they're going to be blown apart. What about the next 5? Well, chances are, after these react, it's going to blow these apart. And what happens is the smaller molecules are going to fly off and not have a chance to react. So, a lot of times you need to make something in slight excess. If you're dealing with liquids, it's fine, but when solids, it's, especially rocket fuel like that, it's weird and doesn't work that well. A lot of this is trial and error, but it's always good to start with this is called the stoichiometric ratio. Stoichiometric ratio.